Okay, so for the second talk of this afternoon session on classical geometry, let me introduce you Miguel Sanchez from Panay, who will talk about something even more classical than the cone structures and the application of fundamental theories of discretization.
Thank you to Felix and all the organizers for this nice meeting and for this opportunity. Well, I am going to speak about this topic, essentially giving you three things. One is some background on cone structures, including Fischler metrics and Lorentz-Fischler ones. Then to share some prospects on fundamental physics and discretization, and finally to explain briefly some ideas on Fermat principle and Snell law, which will be useful for this discretization. About cone structures, well, what I am going to say is common knowledge. I point out these two references with Cavalogias because in one studies the Fischler case, in the other in the Lorentz-Fischlers, some of the ideas that I will just suggest they are developed in depth. About Fischler metrics, consider, for example, the anisotropic propagation of a wave, let's say, in the sense that at each point, the wave can propagate in each direction with a different maximum speed, okay? It is not hard to check that from an effective way, the propagation is the same one if we consider the original hypersurface of velocities than if we consider the convex hull, okay? And so we will have such as convex hypersurface of velocities. Notice that the zero vector is not in the center, and because perhaps going in one direction is different to go into in the opposite direction. Okay. About convexity, there are, for hypersurfaces in a finite dimensional, a finite space, there are essentially three notions. One is convex, which means that the second fundamental form is positive definite and permits for having, for example, a flat part in the hypersurface. The second one is strictly convex. That means that the tangent space only touches at one point to the hypersurface. And the other one is strongly convex, which is with the second fundamental form, positive definite. The convexity of the hypersurface, in the case that it is the closure of a compact domain, then is equivalent to the convexity of the interior of the domain, meaning that if we consider 2 points PQ in any of the domain of the boundary, then the segment joining them lies in the interior in the case of strict convexity, in the interior or the boundary for convexity. Regarding this hypersurface as the unit sphere or indicatrice of a norm, or indicatrice, we can consider a norm which has this hypersurface as unit sphere. Indeed, it is a non-symmetric norm, which is positive with the equality to greater or equal to 0, with equality only at 0, which is positive homogeneous. That means that it behaves as a norm taking out the scalar when the scalar are positive, okay? And this permits to define the norm from the indicatrix. And satisfying the strict triangle, the triangle inequality, which becomes equivalent to the convexity of the indicatrix because of some elementary construction by using a parallelogram. Indeed, triangle inequality and the strict triangle inequality belongs equivalent to convexity and strict convexity. A norm is never smooth at 0. The square of the norm is smooth at 0 if and only if the norm comes from a scalar product. And in general, we will consider norms which are smooth away to 0. Okay. Then this permits us to define sort of nonlinear flat map between the space and the dual of the space, mapping for each vector in the indicatrix, the one form, the vector is V, the one form is V star, says that the tangent, the affine tangent space to the hypersurface, okay, correspond with the vectors such that the one form on n is equal to 1, okay? In the case of a strict convexity, this is a bijective map. And in the case of a strong convexity, this is a diffeomorphism, and this norm is called a Minkowski norm, okay? This will be the regularity we are going to use, but the things can be weakened, but it is the simplest case. So we will consider Minkowski norms, which are positive homogeneous, smooth outside zero, and says that the Hessian of the square of the norm, okay, is positive definite, okay? This condition is just because this Hessian is essentially the second fundamental form of the indicatrix of the norm, okay? And it depends only on the direction of the vector we are considering. Well, a Fiedler metric is then to put a Minkowski norm varying smoothly with the point, okay? We will use the notation R equal to the square of the norm. And at the end, the Fiedler metric is just a function from the tangent bundle to R, which is smooth outside zero, is positive, is positive two homogeneous because we are taking the square, and it has the positive definite fundamental tensor, okay? At its point. In a Fiedler metric, we can define the length of oriented curves, just integrated the norm of the velocity. This is invariant under monotonically increasing parameterization. So we reparameterize in the other way around. Perhaps the distance, the length is different. So we have a non-symmetric distance associated to this Fiedler metric. We can define also geodesics, consider the Euler-Lagrange equation, and then the corresponding Christoffel symbols. They are computed in a way formally similar to the case of Riemannian geometry, but now they depend on also on the velocity, on the oriented direction of the velocity. Well, also locally, this geodesics minimize the distance. From this, one can construct a spray, a canonic nonlinear connection, but I will not go into these elements. Well, what about if we consider that the velocities of propagation do not include the zero vector? For example, we have a wave or a zeppelin propagating in the air, and the air is so, the wind is so strong that we cannot go in the opposite direction. In this case, we have an indicatrix like this, which has a convex part, and associated to this, we have a triangle inequality, and also a concave one, and associated to this, we have a reverse triangle inequality. Okay, because the curves here, if I go in the direction opposite to the wind, I can retard it as much as possible. Okay. This concave hypersurface, regarded as the unit vectors for a positive homogeneous function, can be regarded as a Lorentz norm. Okay. Indeed, if we consider these indicatrices here, okay, just hypersurfaces like this, we can call them wind norms, just compact, strongly convex, compact hypersurfaces, and they will be true Minkowski norms depending if the zero vector is inside or not. Okay. A wind Fiedler metric will be then to put a wind norm at each point. Well, this is the first steps about a fast course on Fiedler elements. Let's go now to the cone structures. For this, I will start with the wind Fieslerian norms. Okay, I will put one at each point of the manifold, and now we look for the propagation after a time equal to 1. Then in a natural way, we will obtain a cone, okay? This is nice because here, on the one hand, the cones are regular for any given Fislerian norm, okay? But we have some type of desingularization of Fislerian structures. And we can also consider possible time dependence of velocities. In general, a cone has a definition, which at the end, the important point for us is that the cones will be strongly convex, in the sense that the second fundamental form is positive, definite positive, except in the radial direction. And they are always constructible as before. Now, a cone structure on a manifold is just to put a cone varying smoothly with the point. And this extends naturally the future cones in general relativity. That is, we have an interior of the cone which is convex, and the time-like vectors live there. We have the vectors on the cone, and the causal, which are time-like or light. We can define, as we have said, all the notions of chronological future, causal future, the orismos. The orismos is the causal future minus the chronological future, and all that. Associated to the cones, we have cone geodesics, which are curves which are locally orismotic. Okay, the generalization of the like geodesics, which depends only on the cone structure. Well, a cone structure can be defined, can be described nicely by using cone triples. A cone triple, omega TF, is composed by one form omega, which is positive on the cone. So this hyperplane, which is the one form over one, intersects transversally to the cone. A time-like vector like this, okay, which is just one form on it is equal to 1, and then taking the intersection on the cone with the hyperplane omega equal to 1 and moving in the direction of t, we can obtain a strongly convex hypersurface in the kernel of the one form. Then in this way, we have a Fislerian area metric in a natural way associated to the cone, okay? Well, conversely, any cone triple will give you a cone. And this way of looking at the cones is nice, especially when we have a time in the space. We have the one form is the differential of the time, and we have the time-like vector can be regarded as the set of observers. Okay. And well, again, this is the first course on cones and the meaning of we are going into the cones. Now let's go with Lorentz-Fisler metrics. Well, here the idea is that we will have a cone, and then we will have a convex indicatrix, which will give a Lorentz-Minkowski norm at its point. And this convexity in hypersurface will be asymptotic to the cone. Okay, this will be the roughly Lorentz-Fisler metric. So this would be the indicatrix, this hypersurface, and then extending this by positive homogeneity is defined on all the cone and the interior of the cone. Okay. This is not the most efficient way to define Lorentz-Fisler metric, but which can be made in a simpler abstract way. But at the end, you have these elements: the cone structure, the indicatrix, which is concave, and the analogous to the fundamental tensor, the Hessian of the Lorentz-Fisler metric, which is regarded as too homogeneous, which will have now Lorentz nature. Okay. Before it was definite positive, so we have a Euclidean scalar product. Now we have a Lorentzian scalar product in each direction. Notice that in this definition, we are defining only on the cone and in the interior of the cone, the Lorentz-Fisler metric. One would prefer to define another Deltanian bundle and just imposing that the fundamental tensor has Lorentz nature. If one make this, just taking a time-like vector, one has a unique way to define a Lorentz-Fissler metric in the sense I have done associated to this vector. Okay. Also, the Lorentz-Fissler metric will give you geodesics, in particular light geodesics, and this light geodesics will agree with the geodesics of the cone structure with full generality. Finally, if we have a cone triple, okay, with this omega and this one form and this Fissler metric, there is a natural way to construct a Lorentz-Fissler metric such that the light vectors for these Lorentz-Fissler metrics agree with the cone structure. Okay. One technical observation is that this construction is not smooth just in the direction of the time-like vector, because in this direction the Fissler metric is not zero. The Fissler metrics are not smooth of zero. But well, anyway, this can be smoothed, and this is not a true problem naturally. The point is that we have always this Hessian with the Lorentz nature for the fundamental tensor. Well, and finally, this is our third element. Again, the Lorentz-Fissler metric. We have the central one was the cones. Previously, we needed the Fissler metrics in order to understand convexity, and now the Lorentz-Fissler to construct and know more about them. Well, where this Lorentz-Fissler metric can be used, okay? As I have suggested, they can use for classical wave propagation, indeed for sound, amplifier, shapes, and so on, and the cone triple is very useful in this case, okay? This is a first application. Also has application for Lorentz-Fissler for Fissler metrics, and also for Lorentz metrics. So for Fissler metrics, because of this desingularization that I mentioned on Wien-Fisslerian structures. And in Lorentz metrics in relativity, because there are some notions as the Wien in Kerr space-time, and so that properly are described by using Fissler metrics. Okay. In relativity and cosmology, they are being used, and perhaps one can think that they may be speculative, but the people which proposed initially this line of research were very non-speculative people. For example, Sheldon Glashow, apart from being a Nobel Prize, have strong opinions on string theory because he was very non-speculative person. Anyway, these Lorentz-Fissler metrics are used in order to face problems in cosmology. But what we are interested here in this meeting is more in foundations on physics, and so more fundamental, taking into account particle physics. And so in principle, from my viewpoint, for fundamental particles, at the end, we will have an emerging semi-classical propagation. As I have mentioned, then we will have cones which will work as an effective theory, and that should emerge in some sense from the theory. Namely, one may think that perhaps these cones could have a more fundamental meaning. And in order to explain why I think that perhaps this is possible, let me mention first the causal sets, which has previously appeared. The causal sets are just points plus causal relations between them, no? According to Sorkin's motto, the number plus order equal to geometry. The background for this is that a Lorentz metric is determined by a volume element, which plays the role of number and the conformal structure of the order. Okay. It's nice that even some decomposition type Gersh type can be obtained in this setting in a conference in the pandemic, but he organized here. I spoke a bit on this. Anyway, these causal sets can be regarded as a extreme quantum discretization, okay? And in an effective or less strict limit, one could think about space-time model by thirds of points with cones. Okay? Indeed, I am going to speak about a non-speculative idea, and perhaps this non-speculative idea can be useful also for these more fundamental physics ideas. Just consider numerical relativity even in real-world discretization of space-time. We, in a natural way, discretize the space-time by taking a grid that again at its cells the metric at one of the points, and then considering this space. What I propose is to discretize just taking on the one hand the cone and the other the conformal factor. The conformal factor would be more or less trivial. The nice point is to discretize the conformal structure, okay, the cones. In this case, I have at each cell in the grid one cone, okay? And then to make something as this is possible in numerics, is feasible, and is more useful, for example, to obtain like geodesics, as I will mention later, okay? The point is, for fundamental physics, a picture like this could be also be useful. Well, in any case, we will have a problem if we would like to make a discretization of this type, which is how the like geodesics, for example, will behave, okay? Or if they are still locally osmotic in some sense, or if they can help to determine causal futures and all that. Then we are going to see that the answer is positive, okay? But I need to speak a bit about Fermat principle and Snell law, okay? Anyways, clear what I am saying? Okay. Well, about Fermat principle and Snell law, the Fermat principle, Kohner and Perlich work in the origins on this topic a lot. And so I am going to follow here a recent paper posted last week with Miguel Ángel Jabaleyes from Murcia, Stimar Borse from the Technical University of Copenhagen, and Enrique Pendas Redondo from Oviedo. The Fermat problem for a cone structure is as follows. Assume that we have a cone structure, we have a point, we have a time-like curve, perhaps with a time, and this is parameterized with a time. We can consider for points starting at the point, the arrival time functional here at the curve, okay? Just measuring the time of the, which parameterizes the curve, the time-like curve at this point, okay? The Fermat principle, or a theorem, says that the critical points of the arrival functional, okay, for this space of curves arriving here, of like curves arriving here, are the cone geodesics from the point to the curve. This can be done as the very general hypothesis. If you look at the paper, you will see that this can be made in a much more general way. Also, there are results on existence of geodesics and on multiplicity and all that. But I will not go into these ideas, but just I will focus on discretization. Okay. For discretization, this is as considering this continuous medium, and this sounds to the classical Snell law, okay? The elementary idea that the light, when it goes from air to the water, well, bends, okay, here, okay? So we are considering now a Fermat problem as before, but for this continuous media. Now the picture is as follows. We have here an interface, okay, and two cone structures, one at each side of the interface. Now the point, point is the following. We start here with like geodesic, it will arrive to this term like alpha, but how it behaves here in the intersection point, okay? The solution, the essential solution for this problem is as follows. If we have here an incident direction u, then this will have, as this is like light, this will have a hyperplane tangent to the cone along it. This hyperplane will intersect the interface, the tangent space to the interface in a subspace. The point is that this subspace must be equal for the incident trajectory and for the refracted one. Okay? This is a nice way to see this classical Snell law. Well, this is the essential Snell law, but there are quite a few also subtleties. For example, the hyperplanes that I have mentioned are naturally oriented by the cones, one on one side and the other side, and so when the orientations do not match, then this cannot minimize. Okay. Also, there are classical issues associated to this. For example, non-transverse incident direction or non-transverse refracted one, and this happens even at a classical level, total refraction and so on. Moreover, here we have possibilities as two refracted trajectories, which are just exclusively Lorentzian. Okay, there are no something as this in the classical setting, or even more that the cones are in the one in the or direction opposite to the other, and there are no refracted trajectory. Anyway, what I want to mention is that all this can be handled, and then at the end one has that in discretized spacetimes like geodesics are consistently defined. The horisontic ones are tightly determined. They determine causality, and so we can work well. So the point is that, well, in general relativity numerics, this can be done and is more effective than other procedures of discretization for some topics. This can be also done for classical mechanics. Indeed, the propagation of seism is a natural way for this discontinuous medium. And the point is, if fundamental physics, in order to discuss here, if there are some prospects on this, either as an effective quantum propagation, that I think that in any case this should emerge, or even more as a part of quantum modelization. And well, this is all. Thank you very much for your attention.